blue-white stars, it's ranked. There's a gradient of these spectral class A stars, and it's the top of its rank. It's almost a B and O star classification, but it's A0. And then the last number 5 refers to its brightness. So in the ranking of the A0s, it's a 5. Anyway, A0 is a much bigger type of star than our sun. It's 2 to 4 times bigger, somewhere in that range, and those stars have so much more mass. They're very, very hot. And it turns out to see these hydrogen lines well, and the A-class group have very conspicuous looking Balmer lines. So there's a whole series of hydrogen absorption lines in these spectra. So this spectrum of Vega here has a number of absorption features that we're going to look at. We're going to calibrate this spectrum. We're going to find out the wavelengths that these lines correspond to and confirm that that's hydrogen. There's one in the red. So that one in the red, where my pointer is roughly, that black little line in the spectrum, that's hydrogen alpha. That, when it's an emission line, that's giving the red color to all of these beautiful nebulae that we look at, like the Swan, and the Eagle Nebula, and the Orion Nebula. It's a very abundant element, hydrogen, and ionization of hydrogen gives that red color, and that's where we're seeing it. Already my spectrum shifted a little bit, and I have to put a new line down here. All right, so that one would be the hydrogen alpha, and there's a whole nested series of so-called Balmer line spectra. This hydrogen has several different groupings of these absorption lines in the spectra. The next group in the short direction is called the Lyman group, and the Lyman lines are ultraviolet, and they don't show on our graph here. Yeah, the line it's a very turbulent night up here in Leesburg. You can see that spectrum dancing around. That's the wind blowing, and then we've got turbulence up above, and that's not helping. One thing I can do is do an average of frames, and I don't think I'm averaging right now. We're just looking at the raw video rate. This is an exposure time of only about 150 milliseconds. And the gain is down. So I still have, as the star starts to set, it's going to get dimmer and dimmer. And if I grab the gain, I can improve it. I have it under video mode right now, so I guess if I were to move the gain, let's see what happens. I got to clear off the markings and then grab the cursor, and then I can take a look at this. So that's helping. And now we can see those vertical, the little black bands in the blue and violet end of the spectrum. That's where most of the action is for hydrogen. When the spectrum gets wider, the line shows up better. Yeah, and you'll see a nice version of that when we get going here. I might leave it right in this area here for right now. So let me explain what we're doing. I got interested in looking at the spectra of stars, and then there was an ad published in Astronomy Technology Today for RSpec. And RSpec is software for analyzing the spectra of stars. It's been written by Tom Field. He has his own company he set up out in Seattle. And he does some work for Sky and Telescope as well. And he obtains these what are called blazed diffraction, and then analyzing the spectrum, you can know different features of the spectrum, and you can compare different stars. You can look at other interesting objects like supernovae and planetary nebulae if they're small. The objects have to be a point, like a star. And I have a couple of figures that I brought with me. One is this figure. It just shows what happens when light comes in at a diffraction grating. So let's pretend it's the light of Vega coming in. And what you see is that light comes in here from the left and hits the grating. The grating is just a transparent plastic or glass matrix that's got very fine milled lines. I guess there's 100 milled lines per millimeter on this grating, or maybe it's per centimeter, but I think it's per millimeter. And the spacing of these lines is so fine, and that's these little white, this ladder of white lines. So this is the grating. It's a transparent grating, and light goes right through the grating, but it's broken up. Some of the light does not interact with the grating at all and goes straight through, and it becomes this central spot, the image of Vega in the focused image. The focused image is right over here at this location. Okay, so we have the light coming in, and then the light only propagates in directions that give constructive interference. So it tends to go in these directions. We have constructive interference, and they can be focused as little spectra according to the wavelength on the camera or on the viewing screen. So here you can see purple is violet is facing in towards the central position, and red is furthest away. And the particular grating that we have is called a blazed diffraction grating. And what it does, instead of taking all the light and throwing it out into all these different spectra, this sketch is just showing the prominent spectra for the first order spectra. And that we're looking at one of those spectra. And then there are secondary, and there's tertiary and quaternary spectra that go off like that. So the light is really effectively thrown off by that grating into a series of spectra. And the neat thing about our blazed diffraction grating, so let me bring that one up. Our grating is not just simply slits. It's more complicated than that. There's the spectrum of Vega again. Now let me get this other one. Here's the blazed grating. Here's what a blazed grating looks like. It's actually very fancy, more than just slits. It's actually a flat, beveled surface like that. It's flat and planar, and all these little prismatic wedges are all angled at the same pitch. And they tend to, the blaze means there's a favored wavelength in that first order spectrum where the light is going to be not only diffracted in this direction. Let me get my pointer back again. So the light would be coming in from this direction, like that. And then it comes through the transparent grating. It gets broken up and diffracted. And this is one of the directions of the diffraction. This is another one. And there'd be another one here, and so on. Like that. But in addition to the diffraction, there's actually 2.3 plus, and I have a MFR5-2 focal reducer, and I have a 5mm spacer, and I have the grating screwed in the end. So in terms of equipment, you couldn't get simpler. Oh, Jack, my whole career is about diffraction and about microscopes, so I really know this stuff quite well. Anyway, I couldn't resist talking a few words about it. Yeah, my day job was not in astronomy, it was in microscopy with microscopes, so I had a lot to do with digital imaging and wrote a book on it. All right, well, so let's see what we can do to take a look at the spectrum now, but in RSpec. So I'm going to retire Downchem Sky. It's gone, and I'm going to pull up now RSpec. And RSpec means real-time spectroscopy. And I'm going to go to live camera. And then I've got to adjust your view in KVY Cam. Hang on a second. Okay, so I'm going to adjust your screen so that you see the profile of that spectrum. There. So there's the spectrum. Let's see how this looks on my Sky Network screen. Let's see what I can do to make that look better. One thing I can do is start averaging a few frames so it doesn't jump up and down so much. That'll quiet it down. And I can already see one of the peaks that I was wanting to see, and that's up toward the top, right up in here. This little, on the left side of the peak there, that little divot, that's the hydrogen beta line. And then I see down here the hydrogen gamma line. And I see the hydrogen delta line. I can see these lines already in the spectrum, so we should be able to get a good result here. So what this is a picture that shows us this spike here is Vega. This is the star Vega. It's a faint version of Vega because most of the light has been scattered off into the spectrum over here to the right. Well, there's a cloud going overhead. I wasn't counting on clouds. Let's see what happens here. It's getting brighter again. I'm going to quick run outside and take a look and see what the story is regarding clouds. Just a minute. So I see it pop back into view again. Okay, so I think maybe what I'll do is try and capture a picture and then we'll analyze it. So I do that on within RSpec, although I could import a Malcam spectrum from Malcam Sky. It'll give me my cursor back, and here we go. Whoops, cloud again. So if it's going to be ornery, maybe what I'll do is just go to image and open up a an image that I have of Vega. I got some last night, so this is an image of Vega. So now we're looking at a still image that I exposed last night. And there are a pair of horizontal defining lines that you flank the spectrum with to control. Maybe you can see the spectrum there on the left. This is the RSpec screen now. And you see those lines up above, the orange lines above and below the spectrum. So I can move these lines. And the active area of analysis is going to be between the two. The more that I separate these away from each other, the noisier the spectrum is going to get, because I'm including a lot of, you can see the background, how it increased. So it's cleaner, a lot cleaner if I can just limit the area in which I'm going to be extracting the data for the curve. And what the curve is just the summation of all the vertical columns of pixels. So those pixels are summed and then plotted. And you'll notice the graph, I don't know if you can read it on the bottom, it says, it does say pixel down there. So let me see. I go like that, it's going to be a better looking graph. Yeah. And let me see, I need to move this, and then I need to take a look at KVYCam. A lot of juggling here. Well, that's not too bad. Okay. So grading, says Bruni, came with 2 spacers. Did you use both? I didn't buy any spacers. You could buy some spacers if you needed. I had so many spacers from Rock and Jack from the cameras that I had that I didn't do that. Okay, so our task now is to convert the pixel axis into angstroms or nanometers. So I'm going to do that right now. And there's a tab down here I picked called Calibrate. And here's my calibration screen. And it asks me to calibrate 2 points. The yellow box is for clicking on the pixel for the 0th order term. So the 0th order is the central order. That's this area here where the Vega image is. And I'm going to increase the size of this so I can see it real good. And then I'm going to click on the very tippy top. And a number has plopped into the box there. And then it's asking if it's 0 order, and I check the box. This is for 0 angstroms on the spectrum. So we already did one. And then the only other thing I have to do is pick a feature on the spectrum. And I'm going to pick this Balmer gamma line right here. So I'm going to expand this region. And you can see the pixel number that's showing right there. So I'm going to click on that like that. And I know that the nanometers that corresponds to is 4340 angstroms. That's it, and I apply. And now magically, the spectrum is converted into angstroms. Oh, Jack is asking about the filter. The filter is 1 1/4 filter threaded. Yes, it is 1 1/4 inch. So it just threads right onto the end of the MFR5 focal reducer like any of our filters would. That makes it very convenient. And the grating is protected by 2 cover slips, front and back, so that you're not going to damage the grating. It's not exactly robust, but you don't have to baby it terribly. Okay, so now we have a calibrated spectrum, and that's exciting. I can get rid of this, and I can now look at some of these features, and I can check and see if they are in rough agreement. So 4333, yes. And I know the beta's up here. 4862, 63, yeah. And this, I think, is the hydrogen alpha, 656. Yeah. So now we have toys that we can play with. So up here on the top of my menu is a little tool for looking at and identifying the different elements in the spectrum. So now that we've calibrated everything, I really don't need to see Vega anymore, and I want to give more attention to the spectrum. So let me do that. Got to move this palette over to the side. Can't grab it. Ooh. Okay, so I'm just going to grab the spectrum. Well, I think what I have to do is first put down the hydrogen line. So here's a marking of the absorption features in the spectrum that we think belong to hydrogen. And now I can magnify this. Put a box around it and spread it out. And you can see we did a pretty good job. If I can somehow, I'll have to move this away. Maybe I will just do that and open it up again. I can't grab a hold of the damn thing. Hey, well, good to see you there. So now that we've gotten our bearings here roughly with hydrogen, now how am I going to move this darn palette? It's just stuck. Oh well. And looking at these absorption features, I don't want that, I want these. And I want to magnify it. Got to be able to see it. I can come back to calibrate, and I can type in my dispersion. So an important feature of all this is given on the top of the graph up here. It's called the dispersion. I think I blocked it out from your screen so you're not seeing it. But it says angstroms per pixel, and you should be in the range of somewhere from 10 to 20. And right now I have a reading of 13.1 angstroms per pixel. So the way that you know that you're getting the spacing and the arrangement right for your grading and your telescope and your optics. Palm Field has a little calculator tool, and you enter in the focal length, you enter in your pixel size, you enter in the dimensions of your sensor, and you can play around with different focal reducers, and you can figure out what length you need. It's pretty straightforward. So if you go on his site for RSpec, you would find this calculation tool. So I made sure that my camera, my DS 2.3 Plus, with my telescope was going to work for getting spectra that could use the software. That was the first thing I did. And I used that calculation tool to figure it out. All right. Well, so what I'm going to show you now is that you can tweak this. I can move those absorption lines around by this slide. There's a slider I'm moving. Let me move this on top so you can see too. So that little blue dot marks a slider, and I'm going to slide it now so that I really am slid so that I've got everything perfectly aligned as good as I can get it. That's pretty good right there. That's 12.94 angstroms per pixel. So I'm going to leave it right there. So I'm going to apply that and close this. And then I am going to expand this view. Like this. I wonder why I'm stuck with this. Oh, there it goes. Okay, good to know. Okay, got that out of the way. And I don't know if I'm quite happy. Let me go back and undercalibrate and tweak that one more time. That's looking pretty good. Maybe I'll put down about 13 and just leave it at that. Okay. Anyway, you got the idea. That's called the calibration of your spectrum. And of course, one thing that you see immediately is that in our spectrum of Vega, we have Vega is a very blue star, and our camera is not very blue sensitive. So this whole region is a strong downslope here, where in fact in the corrected spectrum, these values of the curve continue to ascend. So you wind up with an upsloping curve at the very left end, not downsloping like it is here. This shows that our sensitivity is gone, and we're ended here by about 3,600 nanometers, angstroms. But in fact, Vega's spectrum goes on and on, well down into the violet and ultraviolet. But we can't pick that up. But nevertheless, we do a pretty good job, and you can see that we can see most of these lines. There's another tool here that where we can see details. And if I get rid of my markings here and go to the cursor, we can look at that. It's right here. So there's this nice little palette where we can look at these emission lines. Here's the hydrogen alpha line right here, and that was the little black band we could see in the live spectrum of Vega. Pretty prominent. Here's the beta Balmer line way up here at the top of my spectrum. And then here's the gamma line here. So it's not this dip here, but this dip here. That's the gamma. alpha, beta, gamma, and here's delta right here, right next to gamma. And then there's even an epsilon we can pick up right there. So the visual spectrum's got a number of neat lines, and the gas, the hydrogen and helium of Vega and other A spectral class stars are so excited, so hot, that hydrogen is well ionized. It's a difficult gas to ionize. Stars need to be quite.
Maybe I'll have some root beer.